Okay, yeah, let's resume the class. So we are going to check out, okay, why the set of positive rational numbers is countable. But before that, let us show this very simple theorem. So this theorem says if a set A is countable, then any subset of A, so if you pick any subset of A, then it will also be countable. So the proof is easy. So you need to recall what is meant by countable. Countable means either it is finite or it is infinite, but there is a one-to-one correspondence with n. So there is case 1, if A is finite. So if A is finite, then what does it mean? Then any subset of A is also finite, right? If A is finite, it has, let's say, k items. Then any subset of A has less than or equal to k items. So it is finite. So in that case, yeah, the subset of A must be countable. If you're OK with this, could you please raise your hand? OK, good. So finite, OK. Infinite. So if A is infinite, but then A is countable, then that means what? So that means that the items of A can be listed out one by one. You can list out the item of A, let's call it A1, let's call it A2, let's call it A3, and so on and so forth. It can be listed out so that A1 is the first item that is corresponding to the natural number 1. A2 is the item of A that corresponds to the natural number 2, and so on and so forth. So if I have a subset of A, so let's call it C. C is the subset of A. So C is the subset of A, then I can list out the items of C according to this order. So I check whether this is in C or not. If this is in C, then I will list it out. If it is not in C, then I will not list it out. If it is in C, then I will list it out, and so on and so forth. Is that okay? So what I'm going to list out the items in C is in the order that they are listed out in A. Is that okay? So you can list out C, C1, C2, etc. So the C1 is the first item that is in C that will be listed in A. Is that okay? And C2 is the second item in C, is an item in C that will be listed in A as the second one. Is that okay? So what does it mean? It means that, okay, if there is a labeling for this as 1, 2, 3, 4, 5, 6, 7, and if I have a C, which is a subset of A, then you can imagine what? Imagine C as, so what is C? So to create C from A, C is you just cross out some item that is not in A. That is not in C, sorry. So you just need to cross out some items. And then you can still list out the items one by one, starting from left to right. Is that okay? So if you can list out these items, no problem. This is the first item, the second item, the third item. So you can think of this as this is the first remaining item, the second remaining item, the third remaining item, the fourth remaining item, etc., etc. So in that case, C, all items in C can be listed one by one. Is that okay? Okay, so that's it. So this is the idea. So if A is countable, then any subset of A is also countable. So if you have this theorem, we discussed this theorem much earlier, then you can immediately think about, okay, all the positive even integers, it must be countable, right? Because it is a subset of n. All the prime numbers, it must be countable because it is a subset of n. Okay, and then we have also proven all the integers, positive, negatives together, they are countable. So in that case, you can prove all the even integers, positive or negative, it is countable. You can also prove all the what? All the prime numbers, negative or positive, it is also countable. Okay? Now we have this theorem, so we have the following corollary immediately. So this is just the what? The contrapositive of this one. So So it says that if B is uncountable, then any superset of B must be uncountable. So here it is if P then Q. This one is if not Q then not P. Is that okay? So if the theorem is correct, then this corollary must be correct. Okay, now this helps us. This helps us to prove the positive rational numbers are, so this is the positive rational numbers are countable. So how do we show? I'm not going to show this directly. So let's show this by drawing a table. So this table is like I have 1, 2, 3, 4, blah, blah, blah. And I have 1, 2, 3, 4, blah, blah, blah. So I'm going to have a table like this. Is that okay? So in this table, I write down, this is called 1 over 1. Just a symbol, 1 over 1. You can think of this as January the 1st or 1 over 1, okay? So I have this one as 1 over 2, 1 over 3, 1 over 4. Is that okay? So I have this one as 2 over 1, 2 over 2, 2 over 3, 2 over 4. 3 over 1, 3 over 2, 3 over 3, 3 over 4, blah, blah, blah. 4 over 1, 4 over 2, blah, blah, blah. Is that okay? Is that okay? So if you think of them as rational numbers, then okay, this is 1, this is 0.5, this is 1 over 3, this is 1 over 4. But this is also 0, this is also 1. 2 over 2 is equal to 1, okay? And then 2 over 4 is still equal to 0.5, okay? But let's forget whether they are rational numbers or not. I just think of this as a symbol, okay? Okay, I'm going to say that, okay, so this symbol has this form, P over Q, such that P is in N, Q is also in N, right? Right? So I'm going to show that this set, this is a set. This is a set. This is a set. I choose P in N, I choose Q in N, I get the symbol P over Q, okay? I want to show that this set is countable. Okay, how can we show? So if I want to show that it is countable, then that means that there is a way to list out the items one by one without missing. Okay, so you may think of, okay, maybe I list out this one as 1, 2, 3, 4, 5, etc. But then you will find that this one is going to miss. Because 1, 2, 3, 4, 5, 6, 7. Okay, when will I try to list out this item? There's no way, right? Okay, so this is not a good way to list out the items here. But I want to show that this is countable. So this is my strategy. So I list out this item as 1. This is the first item. Okay, this is my second item. This is my third item. My fourth item. Fifth item, sixth item. Is that okay? So the order that I'm going to list is like this. So like this, a direction, an arrow like this, 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 and so on and so forth. Is that okay? Now, this is interesting. If I list out the items in this way, then every item, any P over Q must be listed. Any P over Q must be listed. It is because, okay, so what is P over Q? P over Q must be listed when, so this adds up to 2, this adds up to 3, this adds up to 4. Am I correct? So there must be an arrow such that it adds up to P plus Q. And before that arrow, all the things there are finite. Okay, so after listing out finite number of items, I must be listing out the row, this arrow, the diagonal, this diagonal that corresponds to the sum of top and bottom part equals to p plus q. And at that time, after some step, I must be listing out p over q. Is that okay? So I will list out 1 over, I will be listing out p plus q minus 1 divided over 1 first, and then p plus q minus 2 divided by 2, p plus q minus 3 divided by 3, and so on and so forth. And at some point, I will be listing out p over q. Is that okay? So this means that using this scheme, every item must be listed. If you are okay with this, could you please raise your hand? Okay, excellent. Okay. Now, so far, I hope you find it interesting. I mentioned already, right? This is difficult, super difficult. And yeah, but this is not the most difficult part. Okay, so it's you're going to see. Okay, so at this point, what do we know? We know that this is a countable set. And then Q plus rational number, all the positive rational number is a subset of this set. Is that okay? So the positive rational number, you can think of this as it is the set such that p and q are integers, p over q, and there is no common factor between p and q. So this q plus, it will just select this element, this element, this element, this element, but not this element, this element, this element, this element, this element, this one, but not this one, but not this one, but not this one, and this one, and so on and so forth. So this is a subset of a countable set, so it must be countable. Okay? Okay, so during the break, a student asked the following question. I think this is very, very good. He asked me, okay, it seems that all the sets here, you can say that it must, all the infinite sets, it must have the same cardinality as the natural number. Yeah, because yeah, it looks like it is quite easy to get a correspondence. But this is not true. Okay, we are going to show this one. The set of real numbers is uncountable. Okay, the set of real number is uncountable. This is a big theorem, okay, super big theorem. Because this problem is only solved within the last 200 years, I think. So this is not an old result, not a too old result, but this is a breakthrough result. Yeah, you can think of, so there is something, so if real number is uncountable, that means what? That means that you cannot establish any one-to-one correspondence between n with this. So it must have much, much, much more thing than in the natural numbers. So it has an infinite thing, more than the infinite that we know. Okay, so this is something very strong. And actually, we can show that the set of real numbers has the same, okay, cardinality as, okay, so if you talk about cardinality, it has the same cardinality as, okay, same size. So it doesn't have the same size as natural number, but it has the same size as 2 to the power n. Okay? So real numbers have the same size as 2 to the power n. And is that okay? Okay. So you can really write down what? The size of n is strictly less than the size of 2 to the power n. Okay? So there is no one-to-one correspondence. The size of n, we call it LF0. Is that okay? The size of 2 to the power n, we call it C. Is that okay? C looks like continuous. So it is called continuum. continuum, something like this. Okay, yeah, there's UU. Okay, so it's like, it's vacuum cleaner. It's like VACCUUM, right? Okay, so this is like UU. There is something like UU here. Okay. Oh, but before we give the theorem of this one, or why this is true, okay, why this is having the same cardinality as this one. So I want to tell you something that is still open, okay. So you look at this is LF0. LF0 looks like it is an infinite concept, but of the base case, okay. So people define also LF1. So LF1 is what? It's something that is infinite, but this is larger than LF0. Is that okay? Does that make sense? Okay. So you can have LF0, and then you can have LF1. LF1 is the next infinite concept. And once you have LF1, you can have LF2, the next infinite concept. Okay, when you have LF1, that means that this is the infinite. So this is the size of an infinite set such that there is no one-one correspondence with n. Okay, and if you obtain such a set, you can define what is LF2. So LF2 is some set that has cardinality strictly greater than a set with LF1, and so on and so forth. Is that okay? So there is concept of LF0, LF1. You can define in this way. Now, amazingly, so far, nobody has found something that is smaller than C and greater than this LF0. So there is a hypothesis. Okay, there is a hypothesis. The hypothesis says C is equal to, so we don't know. It says C is equal to this LF1. So C is the next infinite concept greater than this LF0. Nobody knows, okay? And this is called the continuum hypothesis. Okay, so this is the continuum hypothesis. Good, okay, so if you are interested in these things, infinite and infinite larger than another infinite, then you can check the Wikipedia on this topic, continuum hypothesis. Okay? But now, let us look at this theorem. This theorem is proven by a mathematician called Cantor. Okay? And then Cantor is, okay, we have time. Okay, so Cantor has a very sad story. He proved this result. This looks big, okay? But then at that time, nobody believes him. Even the greatest mathematician at that time doesn't believe him. So whenever he tried to publish his work, okay, in some mathematical journal, someone sees that and thinks that he is crazy, okay? And then we'll put that into the rubbish bin directly. So in the end, he still get published. Okay, so how he can publish a result that people will throw it away? So he go to find a very small journal that no great mathematician will look at. Okay, and then change the title. So from the title, you cannot tell that he's going to prove something like this. Okay, so this is inside a paper in a small journal, and then as a result, they're hidden. Okay, and then so this is what Cantor is about. And then he's also, so at the later years, he has also mental illness. So he's put into a asylum, a mental hospital, and then end his life. Okay, so it's not, okay, it's a very sad story. But his proving technique remains. And then nowadays, we are still using that very often. He's going to use a technique called diagonal technique or diagonalization technique. So let's see. This is a very smart technique that he's going to use to prove this.